Power. Let's start with energy. Energy is hard to define. We all have our ideas about it, such as it's the ability to do work or to cause change by storing energy in one place and releasing the energy to move objects. Maybe the best way to understand energy is by just showing what forms it can take as shown below. So if you'd like, please pause the video here and just look at the various types of energy. And basically this diagram is showing nuclear, mechanical, thermal, electromagnetic, electrical, chemical, and nuclear. And of course there's other different ways that you can organize it. An important concept is not how much energy is available, but how quickly it can be used. How much energy per unit time that can be used is called power. Let's say a box needs to be lifted to a high shelf. That will take the same amount of energy no matter how fast the box is moved. But what if the box has to be lifted very quickly? A very strong person could do it very fast, where a not so strong person would struggle a little and take a longer time to lift the box to the shelf. The strong person had more power to lift the box than the second person. Since power is defined as energy per time, it is represented by this equation. Power is energy over time, or E over T. Since energy is measured in joules and time is measured in seconds, the unit of power is joules per second. In honor of James Watt, who made critical contributions in developing efficient steam engines, the unit of power is the watt, where 1 watt is 1 joule per second. Let's use a mechanical example of power to understand electrical power. Water rushes from a flume, up here, that's a type of pipe, falls and spins a wheel on an axle. The water at the top has gravitational potential energy and kinetic energy as it is moving. As the water falls, its gravitational potential energy decreases as it gets closer to the ground, and some of its energy is transformed into the kinetic energy of the spinning wheel. The amount of water flowing in the tail race, that's down here, below the wheel is the same as the water flowing in the flume. No water is lost. Electric circuits are similar. Current flows from a battery from high voltage to low voltage. When voltage decreases, so does the energy of the current. The energy from the current is transferred to resistors and is also used in motors, light bulbs, heating elements, computers, etc. And similar to the water flow, the current does not change as it moves through a circuit. Electrical power is a specific type of power. It does not involve a person lifting a box, but is used to supply energy to many different processes that will be covered at the end of this unit. The amount of power delivered by electricity is dependent on the voltage and the current in a circuit. Power is equal to current times voltage, or capital P is equal to capital I, capital V. The unit of electrical power is also the watt. If either the current or voltage in the circuit is increased, the power increases. By using Ohm's law and the definition of power, 2 more equations can be derived for power. Here's the first one, which is used when you know what the voltage and resistance is for a circuit element. Here's our power equation, here's Ohm's law. Substitute Ohm's law into electric power, replacing I. So I is equal to V over R. So see right here you have the I. We put V over R in there, just like that. Multiply it out, and we get power is equal to V squared over R. And here's the second one, when you know the current and resistance of a circuit element. Rewrite Ohm's law as V equals IR by multiplying both sides by R. Now we have our electrical power equation, and we have Ohm's law, rewritten a little bit. And we're going to substitute this form into the electric power, replacing V. So power is IV, so here's I, here's V, V is equal to IR, and we get power is I squared times R. Example 1. What is the power consumption of a light bulb that draws a current of 0.5 amps when connected across a 120 volt power supply? Here's our givens, current and voltage, and the power equation is current times voltage. Since the problem gives us the value of I and V, substitute them in to the power equation, multiply them out, and the correct units for power are watts, so our answer is 60 watts. A toy car's electric motor has a resistance of 17 ohms. Find the power delivered to it by a 6-volt battery. This time we have the resistance and the voltage. The power equation, though, is IV. Since the problem gives the values of V and R, use the power equation that relates the power to the voltage and the resistance. And that is V squared over R. Substitute in our numbers, and we get 2.4 watts. A 4.5 amp electric current flows through an electric oven with a resistance of 20 ohms. What is the power dissipated in the oven? This time we have the resistance and the current given. The power equation is IV. Since the problem gives the values of I and R, we need to use the power equation that relates the power to the current and the resistance, which is I squared R. So here's our current, and make sure you remember to square it, times the resistance, and we get 405 watts.